Okay, for what we have for the worksheet problems 5 and 6, neither of these will have a series solution from Maple. And working with what we have for number 5, we'll use as the basis. We have y prime plus xy is equal to 0. And now we have the series expanded notations for y prime and y, and relegating those to what we have in this particular setup. You have y prime, you have c of 1 all the way up to c of 4 x cubed and beyond, and we have plus x times y, and you have c naught plus c1 of x plus c2 x squared c of 3 x cubed, and combining like order terms. So we have the standalone constants going to be c of 1. For the first degree and x terms, coefficients I have 2c of 2 plus c naught. For the x squared terms, I have 3c of 3 and c of 1. And if you notice, lining up, we have this collection of terms equal to 0. And if I set each portion to 0, now again, c of 1 is a standalone constant, so that will become negligible. And anything that ties in with c of 1 and thereafter will also be rendered negligible. So c of 1 is 0. And if c of 1 is 0, we're going to have ultimately c of 3 is equal to 0. And this will carry over to c of 5, c of 7, and c of whatever other odd valued subscript there is. As for what we have with the even subscripted terms, you have 2c of 2 plus c naught. You have 4c of 4 plus c2. And this will carry over to 6c of 6 plus c of 4. And for each collection setting equal to 0, I'm going to take c of 2, c of 4, c of 6, and express in terms of c naught. Now from 2c of 2 plus c naught equal to 0, c of 2 is equal to negative 1/2 of c naught. And if I put this, say, in factorial notation, I have like negative 1/2 c naught over 1, and that translates out to negative 1/2 to the first c naught over 1 factorial. For c of 4, I would have negative 1/4 of c of 2, and borrowing what we have from c of 2, you're going to have, in this case, negative 1/2 times negative 1/2, which would be negative 1/2 squared. And again, you have 1/2 of 1 is going to translate to where we have 2 factorial in the denominator. Now for c of 6, performing the same manner, okay, now we have what's going to be negative 1/2 c of 4 over 3, and adopting what we have already for c of 4, you're going to have negative 1/2 cubed, c naught over 6, and 6 we have at 3 factorial. So for what we have with c of n, this is equal to negative 1/2 raised to the 1/2 n power, and this is divided by 1/2 of n factorial. And we have c naught. And if I get rid of the fractions, so I can convert the n over 2 in terms of an expression that has an integer coefficient, so I can get rid of the 1/2 multiplying by 2. And if I project n on out to 2k, c of n becomes c of 2k, and that's going to be equal to negative 1/2 to the k over k factorial c naught. And then taking what we have here for the general solution, we have y is equal to c of n x to the n as n goes from 0 to infinity, and letting n be equal to 2k, I have c of 2k times x to the 2k as k goes from 0 to infinity. And again, for c of 2k, extracting the c naught, putting out at the front of the summation sign, and we have negative 1/2 to the k over k factorial, again half times x to the 2k, and with the denominator at k factorial, I want to make the numerator exclusively in terms of the k degree. So have negative 1/2 to the k for x to the 2k, that is equal to, on the basis of the power property of exponents, okay, we have x squared quantity to the k, and negative 1/2 times x squared. If I sandwich together, I have negative 1/2 x squared quantity to the k over k factorial. And for what we have as the general solution, and we have the constant, and this summation is in reference to e to the negative 1/2 x squared degree. All right, now in taking what we have in reference to Maple, okay, and so we have utilizing. So going to tutors, differential equations, ODE analyzer. Okay, so looking at taking the derivative of y with respect to x, first degree, insert, and again I have plus x times, not just y, but y of x is equal to 0. And if I add this in, and looking at solving symbolically and putting in terms of formal series, okay, I get this result which has the gamma function. And I've already copied this result. And so this is your notation from Maple. So we have, so again, going from Maple notation. Now, again, the denominator has gamma of n plus 1. Translating in terms of factorial notation, gamma of n plus 1 is equal to n factorial. So, and just letting C01 be our C naught, and then everything else have negative 1/2 times x squared to the n. If I convert everything in terms of the nth degree, and you have over n factorial, and so just using Maple's language and putting in terms of what we can use translating from summation to our official function, we come out to, once again, C naught times e to the negative 1/2 of x squared. Now for what we have officially in problem number 5. So if I go back to Maple, instead of xy, I have the quantity of x minus 6 times y. And so if I go back and I edit, and say I have, instead of just x, I have the quantity of x minus 6 times y of x is equal to 0. So I've edited, and if I solve symbolically with the series notation, I get just y of x is equal to 0. So Maple falls short in terms of any kind of series solution. And so for what we have in terms of Maple, okay, this is our result. They have no series solution provided. And there is a pathway that can be created. And you're not required to know this exactly, but I just wanted to lay this out. And I do have handwritten result here. So you have y prime plus the quantity of x minus 6 times y is equal to 0. And now using what we have for y and y prime and writing and expanding, we have y prime plus xy minus 6y is equal to 0. And just taking what we have for y prime, you have x times y, and you have negative 6 times y. So taking the series expansion for y twice with the coefficients of x, first case, and then laying out, so you have c naught x, c1 x squared, c2 x cubed, and we have negative 6 over y. And for what we have in just wrapping everything together, you have your constant c1, negative 6c naught, and then you have a bit of a building block that is done. And I will tell you, this is very complicated. A few years ago, this took me a while to ever get to the solution. So you have C1 in terms of C naught, C2 in terms of C naught, C of 3, C of 4, and we have for y of x. So again, you have C naught plus 6C naught, 35 halves C naught x squared. And now for what we have in terms of factoring, so we have C naught, you have 1 plus 6x, you got 35 halves, 33, and so on. And now, when we looked at C naught e to the negative 1/2 of x squared, this was our result in the summation. And for what we have in expanding, okay, so you have C naught times quantity of 1 minus 1/2 x squared plus 1/8 x to the 4th, and so on. And if I take this into what I have so far for y of x, okay, so I have 1 minus 1/2 x squared, 1/8 x to the 4th, and so on, into 1 plus 6x, 35 halves x squared. And with the long division, this would be your quotient, 1 plus 6x plus 18x squared plus 54x to the 4th. And in factored form, I have c naught, and I have times e to the negative 1/2 of x squared with this expansion. And then we have with the quotient. And this would translate out to the summation as n goes from 0 to infinity of the quantity of 6x to the n over n factorial. So this part translates out to e to the 6x. So we have for our series solution and putting back in terms of the function, okay, we will have that y is equal to c naught times e to the negative 1/2 of x squared plus 6x. Again, to put it mildly, it's complicated.